Picture a jar sitting in an Egyptian tomb, sealed in absolute darkness for more than 3,000 years. When archaeologists unseal that chamber and crack open that jar, what they find inside is not dust, not residue, not the faint chemical memory of something that once existed. They find honey. Thick, golden, perfectly edible honey that has outlasted the pharaoh it was buried with, outlasted the civilization that placed it there, outlasted empires and dynasties and languages and religions that rose and fell while that jar sat untouched in the dark. This is not legend, this is documented archaeological fact. And it raises a question that stops you completely when you really sit with it. How does a creature that weighs less than a paperclip, lives for 6 weeks, and spends its entire life working in the dark produce a substance so chemically extraordinary that it is functionally immortal? The answer to that question is one of the most fascinating stories in all of natural science. It is a story that begins not in a hive, but in a flower, involves chemistry so precise it rivals anything happening in a modern laboratory, and ends in a jar on your kitchen shelf containing what is genuinely one of the most remarkable substances on Earth. Today, we are going through the full process of how bees make honey from the first drop of nectar drawn from a flower all the way to the sealed cell of finished honey that will outlast everything around it. And by the time we are done, you will never look at that jar in your pantry the same way again. To understand how honey is made, you first need to understand why flowers produce nectar at all. Because nectar did not evolve for bees. It did not evolve for honey. It evolved as a bribe. Flowers face a fundamental biological challenge. They are rooted to the ground and cannot move, but they need to transfer their pollen to other flowers of the same species to reproduce. Over hundreds of millions of years, flowering plants and pollinating insects co-evolved together in one of the most successful partnerships in the history of life on Earth. The plants developed nectar, a sweet, energy-rich liquid, as a reward to attract insects to their flowers. The insects came for the nectar and inadvertently carried pollen from flower to flower on their bodies as they fed. Both parties benefited. The plant reproduced, the insect fed. And out of that ancient partnership, through a chain of biological accidents and evolutionary refinements spanning 50 million years, came honey. Nectar itself is a relatively simple substance at the point it leaves the flower. It is primarily water, typically between 60 and 80% water by weight, with dissolved sugars, mostly sucrose, making up the bulk of the remaining content, along with trace amounts of amino acids, minerals, vitamins, and aromatic compounds that vary from species to species and give different flowers their distinct floral characters. Fresh nectar from most flowers is only marginally more complex than diluted sugar water. What transforms it into honey is everything that happens inside the bee, from the moment that nectar is collected to the moment it is sealed into a wax cell in the hive. And that transformation is where the real story lives. The bee responsible for collecting nectar is the forager, a female worker bee, in the final phase of her short life. Worker bees progress through a series of roles as they age, spending their first days as nurse bees feeding larvae, then transitioning to building comb, guarding the entrance, and processing incoming nectar before graduating in their final 2 to 3 weeks of life to the role of forager. By the time a worker bee becomes a forager, she has already done more work than most creatures do in their entire lives. And now she is about to do the hardest work of all. A forager bee on a productive day will visit up to 1,500 individual flowers. She navigates using the position of the sun, the polarization of light in the sky, the Earth's magnetic field, and a memory for landscape features and flower locations that is extraordinary for a creature with a brain smaller than a sesame seed. When she lands on a flower, she uses her proboscis, a long, flexible, tube-like feeding organ, to reach into the flower and draw up the nectar, passing it directly into her honey stomach. The honey stomach is a specialized internal pouch that sits just forward of her actual digestive stomach and is connected to it by a valve that the bee controls. Nectar stored in the honey stomach does not get digested. It is held there specifically for transport back to the hive, and the bee can carry a load of nectar that equals or even slightly exceeds her own body weight on each trip. But the honey stomach is not a passive container. From the moment nectar enters it, chemistry begins. The walls of the honey stomach secrete enzymes, biological catalysts that immediately begin working on the chemical composition of the nectar. The most important of these is invertase, sometimes called sucrase, an enzyme that cleaves the sucrose molecules in the nectar into their component parts, glucose and fructose. This process begins during the flight back to the hive and continues throughout the time the nectar spends in the honey stomach. By the time the forager returns to the hive and begins transferring her load, the sucrose content of the nectar has already dropped significantly, and the glucose and fructose content has risen correspondingly. This conversion from sucrose to glucose and fructose is not simply about making the honey sweeter, though that is one of its effects. It is about stability. Sucrose is a relatively large, complex sugar molecule that can be broken down by bacterial and yeast enzymes, which is to say, sucrose can ferment. Glucose and fructose are simpler molecules that are far more resistant to microbial breakdown, particularly in the concentrated, low-moisture, acidic environment that honey becomes by the end of the production process. The chemistry happening inside the forager bee's honey stomach on every flight is the first step in building the chemical armor that makes honey immortal. When the forager returns to the hive, she does not deposit her nectar directly into a honeycomb cell. She passes it to a younger processor bee through a behavior called trophallaxis, a mouth-to-mouth transfer in which the forager regurgitates her load of partially processed nectar and the processor bee receives it directly. This transfer is not simply logistical. The processor bee adds her own enzymatic secretions to the nectar during the transfer, particularly more invertase from her own hypopharyngeal glands, and then she holds the nectar in her own honey stomach and actively works it. She repeatedly regurgitates the nectar and draws it back in, exposing it to air and to additional enzyme activity in a process that can continue for up to 30 minutes. This extended enzymatic processing adds two more critically important compounds to the developing honey. The first is glucose oxidase, an enzyme that will later react with water and oxygen to produce gluconic acid and hydrogen peroxide. Gluconic acid is responsible for honey's characteristic mild acidity finished. Honey has a pH typically between 3 and 4, an environment so acidic that most bacteria cannot survive in it. Hydrogen peroxide is a well-known antimicrobial compound, and its presence in honey, even in the trace quantities produced by glucose oxidase activity, contributes meaningfully to honey's legendary resistance to microbial contamination. The processor bee is not just processing nectar. She is building a chemical defense system that will keep the finished honey sterile for years, decades, centuries, millennia. After the processor bee has worked the nectar through this extended enzymatic treatment, it gets passed to another bee, and sometimes another after that. Each pass adds more enzymatic activity, more conversion of sucrose to glucose and fructose, more development of the acidic and antimicrobial chemistry that defines finished honey. By the time the nectar is finally deposited into a honeycomb cell, it has been transformed from a relatively simple sugary liquid into something chemically far more complex, but it is still far too wet to be honey. It is still carrying 60 to 80% water, and at that moisture level, it would ferment within days. What happens next, inside the hive, is one of the most extraordinary examples of collective behavior in the natural world. The processor bees spread the nectar in a thin layer across the surface of the open honeycomb cells, maximizing its exposure to the warm air inside the hive. The internal temperature of a healthy honeybee colony is maintained at a remarkably consistent 35 degrees Celsius year-round, a temperature that is deliberately chosen for brood development, but that also happens to be ideal for accelerating the evaporation of water from the nectar spread across the honeycomb. And then the bees do something that has to be seen to be fully appreciated. Thousands of worker bees position themselves over the open cells and beat their wings simultaneously, not to fly, not to travel anywhere, simply to move air. The coordinated fanning of thousands of pairs of wings creates a continuous, powerful draft of warm air flowing through the hive, passing over the open cells of nectar and carrying the evaporating water molecules out through the hive entrance in a stream of humid air that you can sometimes feel and smell if you stand near the entrance of an active hive during nectar processing season. This collective effort, involving literally thousands of bees working in coordinated shifts around the clock, is what drives the moisture content of the nectar down from 80% toward the critical threshold of 18 to 20% that defines finished honey. How long that evaporation process takes depends on the temperature, the humidity of the environment outside the hive, the strength of the colony, and the specific nectar being processed. It can take anywhere from 1 to several days per batch, and the bees monitor the process continuously, testing the moisture level of the developing honey and continuing to fan until it is exactly right. When the moisture level drops to the correct point, the bees know. And what they do next, sealing that honey away behind a wall of fresh beeswax, is where part 2 begins. Walk through any established Amish rabbit operation, and one thing becomes immediately obvious before you even notice the hutches themselves. Everything is clean, not tidy in a casual sense. Surgically clean in a way that looks almost clinical against the backdrop of a working farm. This is not obsessive housekeeping for its own sake. It reflects a precise understanding that most rabbit disease is environmental in origin rather than genetic. Pasteurella, coccidiosis, enteritis, these are the conditions that kill more rabbits in conventional operations than almost anything else combined, and they thrive specifically in dirty, crowded, poorly ventilated environments. The Amish do not treat these diseases after they appear. They eliminate the conditions that allow them to take hold in the first place, which means they rarely encounter the diseases at all. Every hutch is engineered for automatic waste removal. Wire floors allow droppings to fall straight through the structure, while wooden resting boards positioned strategically prevent the sore hocks that develop when rabbits stand on wire continuously. Slanted roofs shed rainfall instantly rather than allowing pooling. Ventilation gaps are positioned to provide consistent air circulation without creating direct drafts on the animals. This is engineering designed to prevent problems structurally rather than treating symptoms after they appear weeks later. The cleaning schedule itself runs with almost religious consistency. Feeders and water containers are scrubbed weekly using lye soap. Hutches are completely emptied and disinfected on a monthly rotation regardless of how clean they appear on the surface. Bedding is changed every few days on a fixed schedule, not reactively when it visibly looks dirty, but proactively before it has any opportunity to become a breeding ground for pathogens. What most outside observers miss entirely is that the Amish are not simply cleaning, they are observing constantly. Every single morning feeding session doubles as a health inspection. Any rabbit showing the earliest signs of illness, reduced appetite, altered posture, unusual stool, is isolated immediately from the rest of the colony. This single habit is what prevents the kind of outbreak that can wipe out an entire commercial-scale operation within days once a pathogen gains a foothold in a crowded, under-monitored system. The processing approach reflects the same waste-nothing philosophy that runs through every part of this system. Rabbits are processed at exactly 10 weeks of age, the precise window where feed conversion efficiency and meat-to-bone ratio both peak simultaneously. The technique itself is swift and humane, a skill transmitted through direct generational teaching rather than written instruction. The complete process from live animal to packaged meat takes under 10 minutes per rabbit in the hands of an experienced family member. Nothing is discarded at any point in that process. Pelts are tanned for use in clothing or traded within the community. Bones are saved and become the foundation for soup stock that stretches a single harvest across additional meals. Even the manure is composted directly back into the garden as fertilizer, closing the loop that started with forage grown in that same soil. Preservation methods used afterward eliminate any dependence on electricity or refrigeration. Smoking, salt curing, and pressure canning allow processed meat to be stored safely for months at room temperature. These traditional methods also improve flavor in ways that simply freezing meat does not achieve, and they create genuine variety across the family diet throughout the year. Pressure-canned rabbit meat in particular keeps for years and provides ready-to-eat protein during the busiest seasons of farm life, when a single day of focused processing work can fill a family's pantry for months at a stretch. Let's sit with the numbers that actually matter here. The average American family spends approximately $2,800 annually on meat purchased from a grocery store. The Amish rabbit system described throughout this video produces equivalent protein output for under $200 in initial infrastructure costs, and then virtually nothing on an ongoing annual basis. Commercial rabbit meat sells for $8 to $12 per pound at farmers markets currently. Organic grocery store chicken runs $4 to $6 per pound. The Amish produce premium rabbit meat for roughly 50 cents per pound once you account for their time investment against the genuinely minimal material inputs the system requires. But the deeper value sits in how completely the system integrates with everything else on the property. Rabbit manure fertilizes the garden that feeds the family directly. Garden waste and trimmings feed back to the rabbits. This closed loop eliminates external purchased inputs almost entirely while simultaneously maximizing what the land produces. Excess breeding stock becomes a genuine income source on top of the meat production itself. Quality breeding does sell for $30 to $50 each within Amish farming networks. Proven bucks with documented bloodlines command even higher prices. Many Amish families fund their entire rabbit operation, and often a meaningful portion of other farm expenses, purely through selective sales of superior breeding stock developed through their own generational selection program. The return on this kind of investment is genuinely difficult to overstate. Initial setup costs are typically recovered within the first full year of operation. Every subsequent year produces hundreds of pounds of premium protein at functionally zero ongoing cost. This is not simply food production happening on the side of a working farm. It is a form of compounding wealth creation, built entirely through biological systems rather than capital investment. If you are serious about building something similar, understand from the outset that this is a complete system, not a matter of acquiring a few rabbits and hoping for reasonable results. The Amish begin with infrastructure specifically designed around their local climate and available space. Hutch construction follows time-tested specifications. Cedar or pine lumber for weather resistance across decades of use. Hardware cloth flooring paired with wooden resting boards. Standard dimensions of 36 inches deep, 30 inches wide, and 18 inches high for breeding does, providing adequate space without wasting material or land. Placement follows the southeast exposure principle discussed earlier, positioned with protection from prevailing winds, easy daily access for care and cleaning, and appropriate spacing between individual hutches to limit disease transmission while still maximizing the use of available space. starting stock should come from established operations with genuinely proven genetics rather than whatever is locally available at the lowest price. Look specifically for does with a documented history of large litters and reliable mothering ability. Select bucks showing rapid growth and strong muscle development rather than animals bred primarily for show characteristics. The full timeline to reach mature production typically runs about 18 months. The first year is spent establishing breeding stock and learning the management routines that make this system function. The second year is when serious production begins in earnest, as the original does reach peak reproductive performance, and their daughters start entering the breeding program themselves, beginning the generational selection process that compounds in value across every year that follows. 200 pounds of meat produced annually at functionally zero ongoing cost. That is what this system delivers when the methods are followed with the same discipline the Amish have refined across 2 centuries of practical, generational experience. This was never developed as a hobby project for weekend homesteaders. It was developed because family survival genuinely depended on reliable protein production through every season and every winter. That is precisely why it continues working when commercial systems built around purchased inputs and short-term efficiency consistently fail. The 3 most common mistakes I see people make when they try to build this system are the ones that kill operations before they ever reach their second season. Understanding them before you start saves you the cost of learning them through failure. Mistake number 1 is starting with too many animals before the management routine is established. The enthusiasm that comes from understanding how productive this system can be consistently pushes new keepers to acquire 8 or 10 does immediately, rather than starting with 3. Within 60 days, that decision creates an overwhelming situation. You have litters arriving before you have learned to read a doe's behavior in the days before kindling. You have grow-out animals competing for hutch space you have not yet built. You have forage demands exceeding what your land can supply before the comfrey and clover plantings have established themselves. And you have a record-keeping requirement that exceeds what you can realistically track without a system you have not yet developed. 3 does and 1 buck for the first full season. That is the Amish starting point for a new keeper regardless of how much land or space is available. Master the kindling management, the weaning timing, the grow-out feed program, and the forage harvest calendar across 1 complete seasonal cycle before adding animals. The person running 3 does successfully for a full year has more genuinely applicable knowledge than the person struggling through chaos with 12 does at the same point in time. Scale is earned through demonstrated competence, not purchased in the startup month. Mistake number 2 is treating the forage system as optional or supplementary, rather than as the primary feed infrastructure of the entire operation. People read about comfrey and dandelion and clover as feed supplements and file that information away as something to explore later after the rabbits are established and producing. This reverses the correct order of operations entirely. The forage system should be established before the first rabbit arrives on the property, not after. Comfrey requires a full growing season to develop the root mass that supports heavy repeated harvest. A clover planting seeded in the same week that rabbits arrive provides almost nothing for 3 months. Dandelion populations on a disturbed soil site take time to establish at densities that provide meaningful daily harvest volume. Plant your Bocking 14 comfrey crowns in early spring of the year before you intend to acquire rabbits. Seed your clover rotation in the same window. Allow dandelion populations to establish across any unmown area on your property through the previous fall. When your first animals arrive, your forage system is already producing at a level that immediately reduces pellet dependency rather than representing a future goal you are still working toward. Mistake number 3 is abandoning the system during the establishment year, when results do not yet match the eventual potential. The Amish approach to this system is explicitly multi-generational in its time horizon. A family that planted its breeding program in the 1980s and maintained consistent selection pressure across every litter since then is running animals that perform at levels a first-year keeper cannot access from commercially sourced stock. That performance gap is real and it is significant, and it leads first-year keepers to conclude that the system is not working, when the actual situation is that the system is working exactly as expected at year one and needs several additional seasons to compound toward the production. Figures that make the comparison with commercial operations so striking. Your first year will not produce 200 pounds of meat from 12 does. It will produce learning. It will produce the foundation of a breeding program. It will produce the first season of a forage system that will be significantly more productive in its second and third year. It will produce your first understanding of which does in your starting group show the mothering behavior and litter consistency that earn them a place as foundation stock for the next generation. That first year is not underperformance. It is infrastructure construction that happens to produce food while it is being built. The complete integration of this system with the broader homestead operation is where the final multiplication in value occurs. Rabbit manure feeding the garden that produces the kitchen scraps, and garden trimmings that feed the rabbits. The comfrey planting producing harvests that feed the rabbits, while its deep root system simultaneously builds soil biology in the planting area. The preserved surplus meat providing protein security through seasons when other food production on the property is reduced. The breeding stock sales, generating income that funds other homestead needs without requiring a separate income stream to support the rabbit operation. None of this requires land beyond a modest backyard. None of it requires equipment beyond simple wire hutches that any person who can use a pair of pliers can construct in a weekend. None of it requires knowledge that a single committed season of attentive observation cannot develop in any person willing to pay genuine attention to what the animals are communicating through their behavior every single day. The Amish did not build this system as a demonstration of what is possible. They built it because it was necessary, and because nothing else available to them produced equivalent results from equivalent resources. That is the standard that 2 centuries of refinement against actual survival pressure produces. And it is available to anyone willing to approach it with the patience and the systematic discipline that makes the difference between a rabbit operation that produces a few meals and one that produces 200 pounds of meat every year. At essentially zero ongoing cost, start with 3 does and 1 buck. Plant the comfrey before they arrive. Keep every record from the first litter forward. Let the system compound across seasons the way it was designed to compound. The families who built this method understood something that remains true regardless of what century you apply it in. A biological system designed correctly and managed with patience produces returns that no purchased input can match over time. That is the Amish rabbit system, 2 centuries old, fully available, completely replicable, and waiting for the person patient enough to build it properly from the beginning.